In this video, I want to go over carbocation versus carboanion stability. So let's say we had this Sp3 hybridized carbocation, and let's say we had this Sp hybridized carbocation. Which one is more stable? Well, let's think about it. We know we'll have a positively charged nuclei. We know all atoms have positively charged nuclei. So now if we have these positively charged orbitals, let's see what happens. If we have an Sp3 hybridized orbital, we know we will have an orbital that looks like this that's positively charged. However, if we have an Sp hybridized orbital, we know we'll have an orbital like this. Because we know Sp hybridized orbitals are closer to the nuclei than Sp3 hybridized orbitals. Sp3 hybridized orbitals are a little further away from the nuclei. So knowing this, which one looks more stable? Well, again, we know if we have this positively charged nuclei and this positively charged orbital, we don't want this positively charged orbital to be all snug and nearby this positively charged nuclei. We know that's not stable. So therefore, this carbocation is more stable because again, regardless, we don't want a positively charged orbital near this positively charged nuclei. However, we have an Sp3 hybridized orbital. It's a little further. This orbital is a little further away from this nuclei, so therefore that's more stable. So therefore, when it comes to carbocation stability, we know that Sp3 carbocations are more stable than Sp carbocations. However, now what if we were talking about carboanions? What if we were talking about carboanions? Which carboanion is more stable, an Sp3 or an Sp carboanion? Well, again, let's think about it. We're always stuck with this positively charged nuclei. However, this is an Sp3 hybridized orbital when this is an Sp hybridized orbital. And again, we know we have these negatively charged orbitals. We know we have negatively charged orbitals. So now which one looks more stable? Well, in this situation, the Sp3, the Sp is more stable. This Sp carboanion is more stable. Because again, regardless, we have a positively charged nuclei. However, now the orbitals are negatively charged. So now we want the orbitals to be nearby the nuclei. And we want the orbitals to be snug and nearby the orbital. So in this situation, the Sp carboanion is more stable. So therefore, the point is you always have to think about the nuclei, and based on the nuclei, you have to think if it's a carbocation or a carboanion, based on the orbital, if it will be stable or not. So now let's talk about substitutions. So let's say we have these three compounds with these carbocations. Which of these carbocations are more stable? Well, first of all, the first rule of thumb is whenever you have resonance, that's very stable. So in this situation, yeah, we have this positively charged carbocation. However, we have resonance. We have resonance structures delocalizing that positive charge. Now, originally that positive charge was localized here. However, we had this resonance structure, so now the positive charge is delocalized. So essentially that positive charge is delocalized throughout this entire the compound. So we know that's stable because, again, we don't like localized charge. We like to spread out that charge. So this carbocation is the most stable. So now that we know that, now comparing these two, now out of these two, which is more stable? So the rule of thumb is whenever you have an alkyl group, whenever you have these carbon-hydrogen groups, you need to know that they're electron donating. So this is an electron donating group, and this is electron donating, and this is electron, and this is electron donating. So we can draw that with these little negative charges, because again, whenever we have an alkyl group, it's donating negative charge. And the way I like to think about this is, again, we know this carbon has these bonds with these hydrogens. And again, we know we have these orbitals with these negatively charged electrons. So if we have all these orbitals with these negatively charged electrons in this orbital and in this orbital and in all these orbitals, we know we have this essentially all these negatively charged orbitals. So that's why I like to think of alkyl groups as electron donating. But the rule is whenever you have an alkyl group, it's electron donating. So again, these are all electron donating. So knowing that, which carbocation is more stable? Well, clearly this one is more stable because again, when we have a carbocation, we have that localized positive charge, which is not stable. However, we have these negative charges to essentially donate negative charge, stabilizing this positive charge, destroying that positive charge, creating a lower charge density, and essentially stabilizing that positive charge that's stable. So therefore, more substituted carbocations are more stable so the more alkyl groups, those alkyl groups are negatively charged, so they stabilize these positive charges. So therefore, this carbocation is more stable than this carbocation. However, what if we had this situation? What if we had these carboanions? And again, let's say we had this compound. Out of all these carboanions, which is most stable? Well, again, resonance always wins. Resonance is always dominant. So again, we have all those resonance structures. And then we even have more resonance structures delocalizing that negative charge. So therefore, this carboanion is the most stable, because again, resonance always wins. So now comparing these two groups, which are more stable? Which carboanion is more stable? Well, again, remember, alkyl groups are electron donating. Whenever you have an alkyl group, it's electron donating. Whether it was an alkyl group like this or an alkyl group like this, it's an alkyl group, it's electron donating. And again, versus this one with its electron donating alkyl group. So therefore, which is more stable? Well, we know this is not very stable because again, we already have that localized negative charge carboanion. We already have that localized negative charge. So we don't want more negative charge being donating, making this even more negatively charged, that higher negative charge electron density. We know that's not stable. So therefore, we know this carboanion is more stable. So less substituted carboanions are more stable than more substituted carboanions. Because again, the point is, so what if we were comparing these two carboanions? Which one is more stable? Well, again, they're pretty similar, but again, we have more alkyl groups. So we have more negative charge being donating. So therefore, if we have this negative charge with all this negative charge being donating, we're creating a really high negative charge density in this carboanion. So that's very unstable. So this carboanion would be more stable. So now the last thing I want to go over are some examples. So let's say we had this compound with this. We've seen these mechanisms where these electrons essentially attack the hydrogen, breaking this bond where these electrons fall in this bromine. So we've seen these mechanisms, and we know there are two possible intermediates. We can have an intermediate that looks like this, or we can have an intermediate that looks like this. And again, we know, for example, if these electrons attacked where this bond attacked, forming instead of looking like this, instead of the bond looking like this, the bond looking like that, and therefore creating a positive charge here, and if forming that bond with the hydrogen, we would form this carbocation. However, instead, if this bond instead bonded like this, creating the positive charge here, we create this carbocation. So which carbocation is more stable? Well, again, we know this carbocation is more stable. We have all these these alkyl groups donating a negative charge, stabilizing that positive charge, destroying that positive charge, and therefore creating a lower charge density. And again, that's stable and that's more favorable. So therefore, this carbocation is more stable than this carbocation. And then again, we know that the bromine would attack. But again, the point is that we would go through this pathway because this carbocation is more stable. However, now making this a little more tricky, what if instead the compound looked like this? What if instead the compound looked like this? And again, so now we would have something that looked like this. Which of these two intermediates is more stable? Would we go through this pathway or through this pathway? Well, again, we have resonance. So even though, yeah, here we have these negatively charged electrons donating negative charge and stabilizing this positive charge, yeah, that's good, but this has resonance. This has resonance, forming those resonance structures, delocalizing that positive charge over a larger region, so a smaller charge density. So this, in this example, this pathway would be gone. So the point is that resonance is stronger than those electron donating groups. So now what if we had this situation? And again, the same thing where we went through that same mechanism. And again, we know there are two pathways we could go. We could form this intermediate, or we could form this intermediate. So which carbocation is more stable? Well, again, this one looks pretty good because, again, we have that negative charge. Well, it's not negative charge, but essentially this negative donating group, see these electron donating groups, because, again, we have these orbitals with these electrons. So, again, whenever we have an alkyl group, we have electron donating properties donating negative charge, stabilizing this positive charge. So this looks pretty good. However, we have resonance with this carbocation, because again, we have resonance. These electrons can scoop down, forming a double bond, spreading that positive charge partially on this chlorine. So therefore, this carbocation is more stable, because again, even though this has electron donating properties, this has resonance stabilizing the positive charge, which again spreads out that positive charge over a larger region. So therefore, this carbocation is more stable. So now this one's a little more tricky, but what if we had this compound? And again, we added some acid. Which carbocation is more stable? And again, we know it could look like this or this. So something important to note is that we have a carbon here and we have an oxygen here. We know oxygen is very electronegative, so it's pulling onto a lot of electron density. It's essentially it's stealing electrons from this carbon and stealing those electrons so that oxygen is getting all those electrons for itself. So now this carbon has an electron deficiency because again, this oxygen stole all those electrons. So we have an electron deficiency on this carbon. So this carbon is partially positively charged. So therefore, we know this carbon is partially positively charged and this carbon is partially positively charged. So now that, we know this carbocation isn't good. We don't want a positively charged carbocation right next to this partially positively charged carbon. We have these two positive charges nearby each other, so that's not stable. However, in this example, we have this partially positively charged carbon with this carbocation, which are a little further from each other. So it's a little more stable. And also, again, alkyl groups are electron donating negative charge, therefore stabilizing this positive charge. So therefore, we know this carbocation is more stable than this carbocation. So again, when determining carbocation and carboanion stability, a couple things you need to look at. And again, the last thing, and again, this now isn't carbocation and carboanion,